Okay, welcome back, and hopefully you did your little proofs for you. Now let's talk about a couple of important features of the proofs as we're looking at them. Now, when you look at the proof, realize that I did pick one side. Now, one of the most common mistakes that I see in students kind of as we are doing proofs, you guys have a tendency to treat these like equations in the beginning without understanding that what you're doing, you're trying to prove this. There's a big old question mark above this. So we can't treat that like an equation until you have proven that they are actually equal to each other. So the other thing is, in terms of format with your transitivity, do you notice that it kind of has this little Z format where you come down and across? You don't need to write, and I'm going to put it in, then I'm going to take it out. I'm going to undo it. But this is something that you don't want to do. That students have a tendency when they come in here to kind of keep going 1 over cosine theta, 1 over cosine theta. It's not necessarily wrong to do that. It's just completely unnecessary. That you don't need to do that work and write this right-hand side each time that you go down. It's understood mathematically that when we have this string of equations set equal to each other with the equals and the equals and the equals, that we get to conclude at the bottom, therefore, the first thing we started with is equal to the last thing in the string of equivalences. And likewise over here. So it's actually just more work for you if you keep writing it down, and I consider it to be bad form. So when you're doing these little mini proofs, you always pick one side, transform it to another side, doing only substitutions and legal algebra until you get to the other side. And that's what it should look like. All right? Now, coming down here to page 2, the next thing that we have is that we're going to look at, once we get an identity, okay, once we have proven it, then we get to use it. And that's the key thing here, that once we know, our example here, that sine of theta is 1 over cosecant of theta, we also get extra identities to use. We're also going to be able to use that sine theta times cosecant theta is clearly going to be 1. We can manipulate this algebraically. So any algebraic manipulation of the original gives us a new identity that we can also use. So I don't have to prove this identity right here. I get it as a consequence of an identity that I have already proven. Okay? Let's come down and let's look at the next set of our identities that we want to know. And that would be tangent theta and cotangent theta. These are called the quotient identities. That's because a quotient is a fraction. And you see that tangent is the fraction of sine theta over cosine theta, and cotangent theta is the fraction of cosine theta over sine theta. Now, as a note on this, before I'm going to prove one of these for you and leave one for you to try as a proof, but these identities work for powers as well. Notice that what I've done here is I've simply added a square onto these, or a fifth power, that you can take these reciprocal or quotient identities and they work for powers. And just to kind of remind you of kind of what we're talking about here, and this is kind of notation. If I have sine of theta equals 1 over cosecant of theta, one of the things that we do is square both sides of an equation, right? So I can take this identity that is a known identity. I'm just going to do a little arrow over here, and I'm going to square both sides of that identity. Okay? That is an equivalent equation to that. Now, there may be some, when we're actually solving, where we create extraneous solutions and stuff, but it doesn't bother us when we take an identity true for everything on the domain and we square it, it's still going to be true for everything on the domain. So when we look at it here, and then this is just a notation thing, we like to move the square to be on the function name just as a laziness, then we don't have to write the parentheses, and we would have that notation. So these two things are equivalent to each other, and it's just a notation thing. Now, over on the other side here, squaring 1 squared is just 1, and then squaring cosecant becomes cosecant squared theta. And so that gives us this new power identity, and that works for any power. So applying a power to both sides does not matter. Right? Now, let's actually do a proof. And now remember, again, we're still using the given from example 1. I'm not going to rewrite it down. This is where you know what you're given, you know what your basis of facts are that you're going to use. So we're going to be given those terminal point definitions. Right, and now what we're going to do is we're going to use the definition and we're going to prove cotangent theta equals cosine theta over sine theta. So again, I'm going to put a little question mark above that because we don't know whether that's true yet. I mean, it's obviously in these notes, but we're going to do it. Remember, my rule was pick the more complicated side. Clearly, a fraction is more complicated than a non-fraction, so I'm typically going to pick the right-hand side. It doesn't always end up being the right-hand side, but it is definitely a lot of times in some of these that you're looking at. So we're going to start with, we write down the side that we're going to pick, which is cosine theta over sine theta. I'm going to start my string of equivalences. And I'm also going to move this up a little bit, mostly because I'm going to go down this time when I do this proof, because I like that format better than going across, because it helps me see what's going on. So the first step is to substitute using the given and substitute your terminal point definitions for cosine, which is x over r, and for sine, which is y over r. All right, so now I'm going to come down. So a lot of times the reason that this is, you should be able to, when you are reading a proof, see clearly what was substituted. That you can see that the cosine of theta was taken out and this was put in its place, so that the reader can tell what you have done. Now, the rule is, all right, and then once we get to this point and we're coming down, again, we're going to start doing some algebra at this point. So we did a substitution in step 1. In step 2, we are going to basically just do the division by a fraction is the same as multiplying by the reciprocal. So we show that work by flipping that in. And then that is going to, a little bit of algebra again, we're going to cancel common factors, x over y, and then we're going to use in a substitution from our given that the terminal point definition of x over y is cotangent of theta. And so our conclusion, so notice again my proof is coming down, here's my first equals, transitive, 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 so we get to conclude, therefore, cotangent theta equals cosine theta over sine theta. And it does not matter that this is backwards or reversed because of the commutative property that's kind of understood on that. All right, now coming down here, we're going to do proofs for another set of identities that are very, very important to trig and equations. And those are what are called the Pythagorean identities. And we have discussed those before. So it is something that we're just going to come back to, but we are going to do the same thing. We're going to prove them, and then we're going to show you all the different forms that you can use. And so what I'm going to do is also kind of another thing about identities. That identities, it doesn't matter what variable you are using. You can do any identity or a variable that you want. So this identity, once we know it's true, it's also true if there was a theta there. It's also true if there was a t there, and so on. That the variable name itself doesn't matter, that they're interchangeable to each other. We also have a tendency to, if the angles are in radians, typically use x instead of theta, but that's not, completely standard. All right, and then reminding you that cosine squared x is really taking the ratio for cosine of x and then squaring it, keeping that in mind. All right, so we're going to prove our cosine squared plus sine squared is equal to 1. Now, I'm going to just remind you of some given stuff that we know when we're looking at it from earlier. And I'm just going to bring back down the terminal points you still have. But I did want to remind you of one more thing here when we were looking at this. This point xy is on a circle that has a radius of r, and that the equation of a circle, which is from geometry, centered at the origin, would be x squared plus y squared equals r squared. So that's going to be assumed as part of our given when we are doing this proof. All right, so let's start our proof. Now again, remember, what we're going to do is we're going to pick the more complicated side. And in this case, I would say the more complicated side is obviously the thing that's got the trig functions. So I'm going to start with the cosine squared x plus sine squared x, and then I'm going to start my proof. Now, this is unnecessary once we get more involved in this, but I'm just going to show it for you guys because we're kind of little toddlers at this writing trig proofs and simplifying, that when you have this cosine squared plus sine squared, that's the same as cosine of x, the ratio squared, plus the sine of x, ratio squared. Now, I will tell you that the one thing that we don't like about this, okay, is you have to recognize that this x right here and this x right there are not talking about the same thing. And so sometimes that when you see things like this, you really want to be very, very careful about this. So maybe we'll call this xy, that's the point that you have. Let's call it x1, y1, just so that we have a little different. You can't name your two kids the same thing. So I'm just going to make that a little different. And this x right here is really talking about the angle theta. So that's the beauty of math. We typically reuse letters, but they mean different things in context. So just thought I would highlight that this x right here is actually theta, okay? So that's why we're going to rename our point as x1, y1. Now, so coming down, I'm going to do my substitution, and my substitution is that the cosine of the angle x is found by doing the adjacent over the hypotenuse, which would be the x-coordinate of the terminal point, which I'm calling x1. Oops, sorry, let me erase that, which is x1, and then over r. And then we are squaring that, plus the sine is y1 over r, and then squared. So we make that substitution. And then we go ahead and we square each of those things, and we notice that we also, depending on how much algebra you're used to seeing here, I'll do it in 2 steps. A lot of times you can condense some algebra as you're going, if you can see where this is. But I basically squared each of the parts of the fraction, and then I see I have a common denominator, so I can write it as x1 squared plus y1 squared over r squared. So I put that together as a common denominator. Now, here's why I did this little beginning given part that we have, which is this. That's the equation of the circle. And since I renamed this as x1 and y1, we'll just add that in. And so when I see down here in this expression that I have this x1 squared plus y1 squared, I know that I can substitute in r squared, and then it becomes 1. And then we are done. So we would say, therefore, cosine squared x plus sine squared x is equal to 1. All right, now while I'm here, let's talk about alternate forms of this identity, because once we have it, we can manipulate it. Obviously, I can do things like cosine squared x equals 1 minus sine squared x, or sine squared x equals 1 minus cosine squared x, and so on. But there's another trick here, is that you can actually take each of this identity and divide everything by cosine squared and get another identity. Cosine squared x over cosine squared x plus sine squared x over cosine squared x equals 1 over cosine squared x, and then simplify to 1 plus sine over cosine is tangent squared x equals secant squared x. And so you see that what I basically got there through my manipulation is the other Pythagorean identity, secant squared x, right here. So this is not a different identity, it's just an algebraically equivalent to cosine squared plus sine squared equals 1. And same for the other